Okay, so in the last video we talked about the factor theorem and the remainder theorem, and essentially a trick to help us find some of the zeros of a given polynomial, because our ultimate goal is to be able to find all of them. We're going to expand on that today and use another trick that will maybe narrow down the amount of numbers we have to look at to see if we can find a factor. So, suppose we have this. We'll go with x cubed plus 4x squared minus 6x. Give me 1 second. We'll go with plus 5. Okay, so I say that's a cubic, there's 3 zeros, I want to be able to find them. I know by the remainder theorem and the factor theorem, if I can find numbers that when I plug them in get me 0, then I'll have a factor or a 0. But there's obviously a lot of choices, and I don't necessarily want to simply randomly pick numbers until I maybe luck out and get one that works. So, there's another rule, it's called the rational root test, or the rational root theorem. And all it says is, if f of x is a polynomial with integer coefficients, like we have there, then if f of x has a rational 0, it is of the form p over q, where p is a factor of the constant, and q is a factor of the leading coefficient. If f of x is a polynomial with integer coefficients, then if f of x has a rational 0, it is of the form p over q, where p is a factor of the constant and q is a factor of the leading coefficient. One thing to keep in mind before we actually use this does not say there are rational zeros. It just says if what you are talking about, the polynomial we're talking about, has a rational 0, then it has to be of the form p over q. So what you do is, you look at a polynomial, that one, and we say, that's a polynomial, it's got integer coefficients, 1, 4, negative 6, and 5. If it has a rational 0, then it has to be of the form p over q. P is a factor of the constant, which is 5. Q is a factor of the leading coefficient, which is 1. And then how we use this, we say, okay, what are my possible p values? What are the factors of 5? They're just plus or minus 5. We have to account for negatives. What are my possible q values? The only factors of 1 are plus or minus 1. Then I find all fractions p over q, which in this case is just plus or minus 5 over plus or minus 1, which just gives plus or minus 5. So if there's a rational 0, it's either 5 or negative 5. Now I can use the remainder theorem. I can plug in 5 or negative 5 into that. If one of them gives me 0, then it's a 0 and I'm good. If neither of them gives me a 0, then there's no rational zeros, and essentially we're going to have to use some other more complicated trick to try to find the zeros of it. In this case, if we look really quickly, if I plug in 5, I get 5 cubed plus 4 times 5 squared minus 6 times 5 plus 5. 5 cubed is 125. 5 squared is 25. 25 times 4 is 100. Minus 30 plus 5. I don't really care what that is, because that's 225. That's never going to give me 0. So positive 5 is out. Now try negative 5. So I get negative 5 cubed plus 4 times negative 5 squared minus 6 times negative 5 plus 5. Negative 5 cubed is negative 125. Negative 5 squared is 25. 25 times 4 is positive 100. Negative 6 times negative 5 is positive 30 plus 5. And then let's see, I get 135 minus 125, that's 10. That's still not 0, which means neither of the two potential rational zeros give me 0. So that has no rational zeros. And we're going to have to try to find some other trick to get this to work. Okay. Which means we get to dispense with that one for right now because we don't know those other tricks yet. But suppose we have this one. We'll say x cubed plus 6x squared plus 7x minus 14. Now I say, well, okay, what are the possible rational zeros? So, I have integer coefficients, so I look at possible values of p and possible values of q. P has to be a factor of 14. What are the factors of 14? Plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. So there's like 8 of them. What are the possible rational zeros of q, the possible values of q? The only factors of 1 are plus or minus 1. Now my possible p over q's, I do all of these divided by all of those, which in this case is plus or minus 1, plus or minus 2, plus or minus 7, or plus or minus 14. Which means I have 8 potential rational zeros. I'm not going to take the time to do this right here, but you would then plug all 8 of those into that and see if any of them give you 0. I know that seems rather cumbersome, but keep in mind these tricks were developed a couple hundred years ago when they didn't have calculators and computers to do this for them. So they had to come up with a way to do it, and this was simply the best thing they could come up with. But just because I kind of set this up ahead of time, I'm going to try 1 because it's the first one. If I plug in 1, I get 1 cubed, which is 1. 1 squared is 1. 1 times 6 is 6. 1 times 7 is 7 minus 14. 6 plus 1 is 7. 7 plus 7 is 14. 14 minus 14 is 0. That gives me 0, which means positive 1 is a 0 of that polynomial. Now I can try the other rational zeros and see if any of them works, but now we're actually going to use a different trick to see how we're ultimately going to kind of combine everything we know. We know how to do division. We're going to do this relatively quickly. I'm going to take my original polynomial, x cubed plus 6x squared plus 7x minus 14. I'm going to divide it by x minus 1. We said positive 1 was a 0, so the factor associated with that 0 is x minus 1. Remember, switch the signs. Now, I'm going to do my division. What do I multiply x by to get x cubed? I'm going to go through this quickly because you guys already know how to do it. X squared. X squared times x is x cubed. X squared times negative 1 is negative x squared. I switch my signs, negative, positive. 6x squared plus 6x squared is 7x squared. That's 0. Bring down the 7x. What do I multiply x by to get 7x squared? 7x. 7x times x is 7x squared. 7x times negative 1 is negative 7x. I switch the signs, negative, positive. That's 0. 7x plus 7x is 14x minus 14. What do I multiply x by to get 14x? 14. 14 times x is 14x. 14 times negative 1 is negative 14. I switch the signs. Positive becomes negative, negative becomes positive. That becomes 0. Negative 14 plus 14 is 0, and I'm done. There's no remainder, which again, I knew because I did the remainder theorem. But now, essentially what I've done is, I've taken the cubic, and I know it's equal to this times this. But this is now a quadratic. That quadratic I can now solve using other tricks. Quadratic formula. So, using the rational zeros theorem, I looked at all the potential rational zeros. I plugged it into the remainder theorem and found one of the zeros. I then did my long division to turn a cubic into a quadratic, and now I can just solve that quadratic using the quadratic formula. This is actually how we're going to solve these. I'm not going to take the time to throw that into the quadratic formula right now. All of you can do that. But once I do that, I'll get 2 zeros from this. I have 1 0 from the 1, that's 3 zeros, that's my cubic right there, all 3 zeros. We will solve one of these out in 1 second completely, but before then, there is one other theorem that we need that we actually kind of already use, even though we've never called it by name. It's called the conjugate pairs theorem. And all it really says is, if a plus bi, a complex number, is a root of f of x, then a minus bi is a root. Of f of x. Essentially, if you get one complex number as the root of a polynomial, then you get its conjugate as a root too. But we actually already know that because when you do the quadratic formula, we always, when we got complex numbers, we would get things like 2 plus or minus 3i. 2 plus 3i, 2 minus 3i. They always come in pairs, which is all this says. But now we can actually solve one of these out. This video is probably too long, so I'm just going to make another separate short video solving one of these polynomials out completely using all of these tricks.